So in this video we are going to discuss the question in thermal and statistical physics which appeared in JRF physical science examination in December 2013. The first question is, consider the melting transition of ice into water at constant pressure. Okay, which one of the following thermodynamic quantities does not exhibit a discontinuous change across the phase transition? Okay, so first of all, here the important point that we have to figure out is that the transition from ice to water at fixed P. This is an example of a first order phase transition. First order phase transition, and that can be governed by described by the Clausius-Clapeyron equation. It's a first order phase transition. Okay, and while going through the course, you might have learned that in a first order phase transition, the Gibbs free energy is continuous, whereas the first order derivative, or in other words, we can say that the first order derivative or higher order derivative, the first and higher order derivatives of G with respect to temperature, they are discontinuous. Okay, so therefore here the correct option is Gibbs free energy, which doesn't exhibit a discontinuous change across the phase transition. So 3 is the correct option here. Let's take a look at the next problem. Two thermodynamic systems are described by the following equation of state. So this equation of states, they are given by 1 by T1 that is equal to 3Rn1 by 2U1 and 1 by T2 that is equal to 5Rn2 divided by 2U2, where T12, N12 and U12 are the respectively the temperatures, the mole numbers and the internal energies of the system, two different systems 1 and 2, and R is the gas constant. Let U total denote the total energy when these two systems are put in contact and attain a thermal equilibrium. Okay, the ratio, so we have to determine this ratio for the given condition. So let's take a look at the things which are given to us. So we are given an equation between the temperature and internal energy and the number of particles in a system. So from this equation I can write the total internal energy of the system 1, which we call as U1, that is equal to, rearranging this expression, we can write U1 is equal to 3 by 2 R N1 T1. Okay, similarly rearranging the terms in the second expression, I mean this one, U2, the energy of the system 2, that is equal to 5 by 2 R N2 and T2. Okay, now when these two systems are combined together, so let's note symbolically these two systems by these two different boxes, where U1 is the total internal energy of this system, and then U2, that represents the total internal energy of the second system 2. Okay, which is at temperature T2, and this is at temperature T1 with N1 number of particle and N2 number of particle. Okay, when these two systems are combined together, so they form a one big system. Okay, and let's say the final temperature of this combined system is T. Okay, so ultimately we have to determine the ratio. Basically we need to determine the final value of temperature, so then it will become a separate question. Okay, so the total internal energy of the composite system, if I call that as U total, that will be simply the sum of the internal energy of system 1 plus sum of plus the internal energy of system 2. Okay, so simply by making use of this equation, U total, that is equal to U1 plus U2, so that is equal to 3 by 2 R N1 T1 plus 5 by 2 R N2 T2. Okay, now we have to determine the ratio U1 by U total. Okay, so U1 by U total, U1 divided by U total, that is equal to, so substitute the value of U1 in the numerator, so that is equal to 3 by 2 R N1 T1 divided by 3 by 2 R N1 T1 plus 5 by 2 R N2 T2. Okay, so R will cancel here because it's in both numerator as well as in the denominator, and applying the condition of the equilibrium. So in equilibrium, the temperature of the both of the systems, they will become equal. Okay, so let's say in the equilibrium T1 is equal to T2, and let's say that is equal to certain temperature T. Okay, so by replacing T1 and T2 with the common temperature T, so ultimately the ratio, that is U1 divided by U total, that turns out to be equal to 3N1 divided by 3N1 plus 5N2. Okay, because then in that case 2 will also cancel because it's both in the numerator as well as in the denominator, and T will cancel. Okay, so let's say which one is the correct option. It is option 2 here. Okay, so 3N1 upon 3N1 plus 5N2. Okay, so that's our correct answer. So let's take a look at the next problem. The statement is, the speed v of the molecule of mass m of an ideal gas obeys Maxwell velocity distribution law at an equilibrium temperature T. Okay, let Vx, Vy and Vz denote the components of the velocity, and K is the Boltzmann constant. Then the average value of alpha Vx minus beta Vy. Actually it should be, okay, let me write it here. What is asked here? It's not written correctly here. Alpha Vx minus beta Vy, its whole square, and what is the its average value. So we have to determine the average value of this expression. Okay, so in Maxwell-Boltzmann velocity distribution we have learned. So let me first share some of the standard results that we learned when we did the theory. Okay, so average of Vx, that is equal to average of Vy, the velocity along y direction, and that is equal to average of Bz, the velocity along the z direction, and that is equal to 0. And another two important results are their cross multiplication, that's Vx Vy its average, and that is equal to Vy Vz its average, and that is equal to further Vz Vx its average, and that is equal to 0. And the third one is Vx square average, that is equal to Vy square average, and that is further equal to Vz square average, and that is equal to Kt by m, where K, that's a Boltzmann constant. Okay, so now we will make use of these results, and then we will try to see what is the final answer. So here alpha Vx minus beta Vy its whole square, and then its average. Okay, that is equal to, so let's expand the square. So this is alpha square Vx square plus beta square Vy square minus 2 alpha beta Vx Vy. Okay, and then its average. Okay, now this can be written as alpha square, but it's a constant, so we can take it outside the average. Okay, So Vx square plus beta square and then average of Vy square minus 2 alpha beta average of Vx Vy. So this quantity it will be 0, okay, and these two quantities they are equal to kBt by m, okay. So therefore combining these two terms we obtain this is equal to alpha square plus beta square multiplied by kVt by m, okay. So therefore option 2 is the correct one here, okay. So let's continue with next problem. The statement is the entropy S of a thermodynamic system as a function of energy E is given by the following graph. So we are given a graph between entropy and energy for a particular system. The temperature of phases A, B and C, they are denoted by TA, TV and TC respectively, okay. So they satisfy the following inequalities, okay. So we have to identify the correct one, okay. So let's take a look at the diagram and try to understand how we can solve this problem. So if we because it's a graph between the entropy and energy, so the temperature is linked with the slope of this curve by relationship 1 by T, that is equal to ds by dE, okay. So that means with the help of by knowing the slopes for these three different curves, we can figure out that which temperature is going to be largest or smaller one, okay. So if we just take a look at these three curves A, B and C, so then curve V it's flat and parallel to the x-axis, which is the energy axis, okay. So that means for this curve ds by dE, that is equal to 0, okay. So for curve B, okay, ds by dE, that is equal to 0 because it's parallel to the x-axis, okay. So this implies T, the corresponding temperature called TB, that's going to be very large, or in other words, by testing this result that ds by dE that's equal to 0, TV it will approach infinity, or you can say it's going to be very large, okay. And this temperature it's going to be larger than TA as well as TC because the curve A and curve C, they are having finite value for the ds by dE, the slope value, okay. So that means TV it's going to be largest for all of these three curves. Now we have to make a choice between curve A and curve C, that which one is having smaller or larger slope. But if you just take a look at the diagram that is given to us, it's not easy to figure it out that whether curve A is having a smaller slope or curve C is having smaller slope, unless until the angles the horizontal curve, if these angles they were specified, then it will become relatively easy to figure out that which one is having a smaller or larger slope. Since it's not given to us, so then what we will do is we will follow an indirect method, which is that the phase which is stable at a higher energy, that will correspond to a higher temperature. So here phase say the internal energy of phase A it's larger than the phase A, so therefore TC is going to be larger than TA, okay, and TV it's going to be larger for among all three, okay. So therefore the correct relationship is TV that's larger than TC and larger than TA. So therefore here option 3 is correct. So let's take a look at the next problem. It is from the Carnot cycle. So a Carnot cycle operates as a heat engine between two bodies of equal heat capacity until their temperature become equal, okay. So let's draw the Carnot cycle and then try to understand this problem. So we are having a Carnot cycle which is operating between two reservoirs having equal heat capacity, let's say Cv, okay, and initially their temperatures they are different. Let's say T1 and T2 represents the temperature of these two reservoir, okay, or the bodies you can say, and in between we are having a cycle, okay. So here a Q1 amount of heat it enters into the cycle at temperature T1, and same way Q2 is the amount of heat which is ejected by the when the cycle is operating. Okay, it's ejected to the reservoir at temperature T2, and during in one full cycle the amount of work done that we obtain, that is equal to Q1 minus Q2. And finally, when the system will keep on going through large number of cycle, and ultimately the temperature difference between these two reservoirs or these two bodies that will reduce, and the temperature for the one of the reservoir it will reduce, and for the another reservoir at lower temperature initially it will increase. Okay, so ultimately a situation will come when the final temperature will be similar for both of the reservoirs. So let's see how we can resolve this problem. So the net entropy change for the cycle, okay, so that is given by delta S cycle, okay, because it's a reversible cycle, so that is equal to delta S1 plus, I will explain what is delta S1 and what is delta S2, plus delta S cycle. So rather than calling this as delta cycle, it's let delta S, it denotes the total entropy change for the this entire system I'm talking about. Okay, so here delta S1 represents the entropy change for the reservoir or for the body 1. Okay, this is the entropy change for body 1, because during the cycle the Q1 amount of heat is coming from body 1 to the the Carnot cycle. Okay, and delta S2 with the entropy change for the body 2. Okay, so for body 2 it's receiving Q2 amount of heat, so therefore for this the delta S2 will be positive basically, because the heat is entering to the body 2 here, whereas heat is leaving the body 1. And delta S cycle corresponds to the entropy change for the cyclic substance, and this is the entropy change for the substance that undergoes the cycle, and this is going to be 0 because when the cycle starts from this point and ultimately it goes through 4 different stages, and finally again it comes back to the same initial equilibrium state. So therefore the net entropy change delta S cycle that's going to be 0. Now basically we have to determine the entropy change for delta S1 and delta S2. So for the body 1, temperature changes from T1 to T. Okay, we are assuming that T is the common final temperature at which the Carnot cycle will stop working. Okay, the corresponding entropy change for the body 1 is given by delta S1 that is equal to T1 to common temperature which is T. Okay, and then dQ1 upon T1, or dQ1 upon T basically, the in general. Okay, where temperature is changing from T1 to T. Okay, so dQ1 it's given by Cv dt upon T from T1 to T, and that is equal to Cb ln T final, which is T, upon T initial, which is T1. Okay, that's the entropy change for body 1. Okay, so for body 1, because T1 is larger than T2, okay, because here we can say that T1 is larger than T2, so therefore the common temperature which is T, so T is going to be smaller than T1 and T is going to be greater than T2, so therefore this the delta S1 it's going to be a negative quantity basically. Okay, similarly the entropy change for the body 2 delta S2 it will be equal to Cv ln the final temperature which is T divided by initial temperature which is T2. Okay, so let's call this as, this is our equation 1, this is equation 2, and let's call this as equation 3. Now the net entropy change during the when the one complete cycle is over, so delta S will be 0 because it's a reversible process basically. So this ensures that delta S1 plus delta S2, that will be equal to 0. And if we add these two terms here, equation 2 and equation 3, they implies CB ln T upon T1 plus CV ln T upon T2, that is equal to 0, which indicates CB ln T square upon T1 T2, that is equal to 0. And this is 0 when T square by T1 T2, that is equal to unity. Okay, so let me introduce a page here. So the entropy is 0 when delta S is equal to 0, when T square upon T1 T2, that is equal to unity. Because when this is equal to unity, so ln 1, that will be equal to 0. Okay, so this implies T is equal to under root T1 T2. Okay, so that is the common final temperature of the both reservoirs. So let's say which one is the correct option here. So option 3 is the correct one here. So let's continue with the next problem. System of n classical non-interacting particles. So we are having n particles which are non-interacting, each of mass m and at temperature T, and they are confined by external potential which is given by Vr, that is equal to 1 by 2 AR square, where A is a constant in 3 dimensions. Okay, so there are a lot of things which are given in the statement. So the internal energy of the system is, okay, so we can determine the internal energy of the system by simply taking either the n particles together, or first considering one single particle, and then we will write the partition function for it, and then we will evaluate the average energy associated with one single particle, and then from there we can calculate the total energy which is associated with n classical and non-interacting particles. Okay, so the information that is given to us is it's the potential in which they are confined. Okay, they are subjected to the potential Vr, that is equal to 1 by 2 A R square. So in 3 dimension this can be written as 1 by 2 A, it's a constant, and inside we will have x square plus y square plus z square. Okay, now the Hamiltonian of the system for one single particle, or for all the particles, that can be written as H. Okay, that's the sum of the kinetic energy and the potential energy. Okay, so for one single particle it is given as px square plus py square plus pz square. So we are making use of the classical expression for the kinetic energy divided by 2m plus the potential energy, which is a by 2 x square plus y square plus z square. Okay, let's call this as equation 1. Okay, now we will write the partition function for one single particle. Okay, that is q1 dv, and because it is in 3 dimension, so this is 1 divided by h power 3n. Okay, h power 3n, because n we are taking it only one particle, so only 3. Okay, and then integration from minus infinity to infinity, minus infinity to infinity, from minus infinity to infinity, and then the exponential minus beta h. So first we will write the terms corresponding to the potential energy. In the first 3 integral, they will correspond to the kinetic energy terms. Exponential minus beta p x square plus py square plus pz square divided by 2m and multiply by dpx dpy dpz, and then integration over the position coordinates. Okay, so that is with the limits from minus infinity to infinity for each integral, and then the exponential minus beta, then now it's multiplied by this term, okay, the potential energy term, exponential minus beta a by 2 multiplied by x square plus y square plus z square, and then dx dy dz. Okay, let's call this as equation 2. So we have to solve this. So what I'm going to do is I will simply illustrate how we can solve this integral by making use of the one of the standard integral, and the standard integral that we are going to make use of that is given by x minus infinity to infinity exponential minus alpha x square dx. Here alpha, it's a constant term here, constant, and this is equal to under root pi by alpha. Okay, so we will make use of this result. So by making use of this result here, I will demonstrate it only for one integral. So integral minus infinity to infinity exponential minus px square, okay, upon 2m kt. So beta, that is equal to 1 by kt, so it will become 2m kbt and then dpx. Okay, so similarly we will have integral for the dpy and dpz. So all these three integrals, they will be multiplied together. Okay, so this will be equal to, so by treating 1 upon 2m kt as alpha, okay, so therefore here 1 upon 2m kt, that is equal to alpha. Okay, so this integral will be equal to under root pi divided by alpha, so it will be basically 2 pi m kbt. Okay, similarly exponential minus py square upon 2m kt dpy, that will also give us 2 pi m kt, and the third integral will also give the same quantity. And same way we can solve this integral also. Okay, here the constant alpha is equal to a upon 2 kt. Okay, so when we will solve this integral, so let me the integral minus infinity to infinity exponential minus a upon 2 kt into x square dx. So here alpha is equal to a divided by 2 kt, so this is equal to under root pi by alpha, so that means this is equal to 2 pi kt upon a. Okay, so therefore this total result, it q1 tv will be 1 divided by h cube as it is. Now here we are having three different integrals, and the value of one integral is 2 pi m kt. So therefore 2 pi m kt power 1 by 2. So therefore for third integral it will be equal to 2 pi m kbt power 3 by 2. So this corresponds to this one. Okay, now for the next three integrals, the result for one integral, it corresponds to 2 pi kt by a under root. Okay, so therefore for three integrals the result will be 2 pi kt upon a power 3 by 2. Okay, so let's call this as result 3, or this can be rewritten as, because here we are having a kt power 3 by 2, and here also in the second term also we are having kt power 3 by 2. So when we will add these two terms, or when we will multiply these two terms, sorry, not adding, but when we are going to multiply these two terms, so kt, it will become kt power 3 by 2 plus 3 by 2, so that is 6 by 2. So ultimately it is equal to kt power 3 basically. Okay, so that means, and clubbing all rest of the terms, clubbing in one single constant. So let me write this result further as, this is equal to c into kbt power 3 by 2 plus 3 by 2. So that is equal to c kbt power 3. Okay, or this is equal to c upon beta power 3. So what is C? So in this term C, I have clubbed all the remaining constants, 1 by h cube into 2 pi m power 3 by 2 multiply by 2 pi divided by a power 3 by 2. So all these constants, they are merged in constant C here, okay, because we have to simply simply find the average energy. So average energy simply depends on the temperature here. So let's see how we can solve this further. So the Q1, so therefore what we have done is we have written the partition function for single particle, that is equal to C divided by beta q. Okay, so this implies ln Q1 dV, that is equal to ln C upon beta q. Now the average energy per particle, that is equal to minus curly beta of ln Q1 dB. Okay, so by substituting the value of the partition function, so this is equal to minus curly beta of ln C upon beta q, and this is equal to minus 1 divided by C upon beta cube and then curly beta of C upon beta cube. Okay, and this is equal to beta cube upon C with negative sign, and then it's the differential of C upon beta cube with respect to beta, so it will give us minus C upon beta 4. Okay, so this is equal to, and then multiply by 3 also, minus 3C upon beta 4. Okay, so that is equal to 3 divided by beta, or simply this is equal to 3 kBT. So this is the average energy per particle, and how many particles we are having in our system? That is n particles. Okay, so therefore the average energy of the system for n particle is equal to n times the average energy per particle, and therefore that is equal to 3n kBT. So this is our answer. So let's see which option gives this result. So it is 3n kT. Okay, so therefore option 1 is correct here. So let's take a look at the last problem. This is basically from the random walk problem. So a child makes a random walk on a square lattice of constant A, taking a step in the north, east, south or west direction with probabilities which are given as 0.255, 0.255, 0.245 and 0.245 respectively. After a large number of steps n, the expected position of the child with respect to the starting point is at a distance. Okay, so we can solve this problem as below. So let's first draw the base directions in which a child can move and the corresponding probabilities along that particular direction. Okay, so if you call this as the north direction, the probability along north, it is equal to 0.255, 0.255. Similarly, the probability along the east direction, it is, so this is the south direction and this is east and this is west. Okay, so along east direction the probability is also 0.255, and along the south direction it is, the probability is 0.245, and also along the west direction the probability is 0.245. okay, so we have to find the correct option, that after, if the child is making n steps, what is the in which direction he is moving basically. Okay, so the average distance for one single step, it is given as r, that is equal to summation ri pi divided by P, it's basically the function of Ri, okay, or divided by P, the probability Ri, and this is equal to unity, so this is basically equal to Ri P Ri, okay. So for given probabilities for the four different directions, so this is equal to, because the step length is a, okay, so if the child is moving from this point to along the east direction, the step length is a, or if he is moving along the vertical direction, it is again a, okay. So let's call this as the positive x direction and this as the positive y direction, and the opposite direction are negative respectively, okay. So therefore this is equal to along the, let's take the probability along the vertical y direction, so this is equal to a, and along the vertical direction we are taking it as the y axis and then multiply by the corresponding probability, which is 0.255, okay. So I'm talking about this direction, okay. Now along the positive x direction, okay, plus a I multiply by the corresponding probability PRI, that is 0.255, okay, and then along the best direction, so okay, so along the best direction the step size, it's again a, and it's along the negative x direction, so minus I, and then the corresponding multiply by the corresponding probability, which is 0.245. So I'm talking about this one, okay. Now the only direction which is left, it's the south direction, okay. So for the south direction, again the step size, it's same, and it is along the negative y direction, so multiply by minus j and the corresponding probability, which is 0.245, okay. Now adding the corresponding vectors here, so this comes out to be equal to a multiply by 0.01 j plus a into 0.01 I, okay, or this is equal to a into 0.01, and inside the bracket we have I plus j, okay. So therefore the mean displacement is, it is along the somewhere in between I and j direction, the positive I and j direction, so that means it's along the northeast direction, somewhere along this northeast, okay. And the magnitude is given by, the magnitude is given by 0.01 a, and then 1 square plus 1 square power 1 by 2, so that is equal to under root 2 into 10 power minus 2 a, okay. So therefore for n steps, the mean displacement will be, let me call that as r, that is equal to n multiply by mod r, the mean displacement of one single step, okay. So that is equal to under root 2 times under root 2 into 10 power minus 2 and then multiply by n a, okay. So therefore the correct option is here, under root 2 into 10 power minus 2, so therefore a is the correct option here, it's along the northeast direction.